Welcome to the Deep Dive. We're here to crack open the latest research and, well, get straight to the core insights for you. Today we're tackling a paper that honestly, it feels like it solves one of the really tough nuts to crack in photonic AI. We're talking about making those light speed calculations rewritable and non-volatile. That's kind of the dream for optical computing, right? Specifically, programmable diffractive deep neural networks, or DDNNs. We'll be looking at a theoretical demonstration using phase change materials and, interestingly, direct laser writing. Our aim here is to give you a really solid professional overview of this whole architecture, the training, the results. We're assuming you've got that expert background in ML, optimization, maybe some integrated photonics too.
That's right. Our mission really is to pick apart how this combination actually works, how it creates a programmable device that functions. And this isn't just, a theoretical exercise. It feels like a genuine technical step forward, tackling limitations that have been around for a while. So we'll get into the material science, the specifics of the training method, that a joint gradient approach, and definitely the performance. How did it do on pattern recognition? MNIST. What are the limits?
Yeah, and what really makes this stand out is getting non-volatility and programmability together in such a tiny package. Photonic neural networks, PNNs, they've always had this promise, right? Super low power, massive parallelism, light speed processing, amazing potential. But the big hurdle was always programmability, adjusting those weights efficiently. Previous attempts, well, they were either fixed once you made them no retraining possible, or they used volatile components, things like thermo-optic modulators.
Right, and those need constant power just to hold the weights. Plus, you get thermal crosstalk issues, especially when things are packed tightly on a chip. Exactly. Constant power draw kind of defeats the purpose if you're aiming for ultra-low power passive computation, especially at scale.
So this new approach, using phase change materials, that tackles the volatility problem directly. It's a physical change, storing the weights. That seems like the fundamental shift we need to explore first.
Definitely. Let's start right there at the material level,
Yeah.
because the choice of phase change material, the PCM, it underpins everything. The programmability, the non-volatility. The researchers went with antimony selenide, SB2SE3.
SB2SE3. Okay. Now, many folks might know GST, germanium antimony telluride, from Memory Tech. What makes SB2SE3 the better choice here, especially for optics in the telecom band? Around 1.55 microns.
Yeah, good question. SB2SE3 is relatively newer in this specific photonic context. Its advantage really comes down to a couple of key performance metrics critical for integrated photonics at that 1.55 micron wavelength. First, it has ultra-low optical loss. Really, really low. Second, it offers a significantly large refractive index contrast between its states. I'll give you some numbers. The amorphous state, ASB2SE3, its refractive index N is around, say, 3.7 to 3.8. But when it crystallizes, CSB2SE3, that index jumps way up to about 4.6 or 4.7.
Wow. Okay, that's a huge jump, a contrast close to 1.
Exactly, and that large contrast is absolutely essential. It's what lets you get the phase modulation you need, but within a physically very short distance, really compact.
Okay, so the high contrast gives you powerful modulation. And the ultra-low loss means the light signal doesn't just fade away as it goes through potentially many layers of these components. Makes perfect sense for fitting into that existing silicon photonics ecosystem, which is all optimized around 1.55 microns.
Precisely. That specific combination, low loss, high contrast, that's what makes it possible to build these metasurfaces that are compact, low loss, and crucially, rewritable and non-volatile right there on the chip.
Yep.
If the loss was higher, you simply couldn't cascade enough layers to build a deep network. The signal would just die out.
All right, let's talk about programming these weights. Direct laser writing, DLW. Now, for anyone who's dealt with, the headaches of multi-layer lithography for making photonic integrated circuits, PICs, using DLW for this kind of nanoscale precision, it sounds almost, well, too easy. How does it actually achieve the resolution needed for these tiny meta-atoms?
It works by focusing a laser spot very precisely onto the SB2SE3 thin film. This focused heat locally induces the phase transition. You're essentially switching between the amorphous and crystalline states right where you point the laser. It's like writing the desired optical property directly into the film. And the paper really emphasizes this. DLW on these films is simpler, cheaper, and much faster than, say, conventional electron beam lithography with all its complex masking and etching steps. Plus, another key point, the phase transition is thermally driven, right? But the operational wavelength, 1.55 microns, it's transparent to the writing laser, which is usually a different wavelength. This means you can read the state non-destructively while operating the device, and you can rewrite it without interfering with the operation.
Hold on a second. You're saying this isn't just about making the initial chip cheaper to fabricate? A laser can literally go back and fix errors on the chip after it's been made. I mean, what kind of correction are we talking about? Is this fine-tuning individual elements?
Yes, that's exactly the potential game changer here. Think about fabrication yields. If minor imperfections are no longer deal breakers because you can correct them post-fab, that suddenly makes the whole approach much more practical, commercially speaking. The source is explicit about this rewriting capability. If there are imperfections, errors in writing, you can locally erase that spot, maybe by heating it differently, and then rewrite the correct state. This is what opens the door to in situ training.
In situ training?
Yeah.
Wow.
Right. You could potentially make the DDNN, test its actual performance, identify where it's deviating, perhaps because of manufacturing tolerances or even inaccuracies of the simulation model used for the design, and then use the laser to physically tweak those specific faulty meta-atoms to bring the performance back up. It bridges that persistent gap between the theoretical design and the messy physical reality.
Okay, let's define the core component, the thing actually storing the weight. The
Right.
meta-atom, the building block, the sort of neuron here. What's its physical structure?
So the meta-atom in this design is essentially a one-dimensional element. It's a small rod made of amorphous SB2SE3, the ASB2SE3. And this rod is embedded within the surrounding thin film, which is in the crystalline state, CSB2SE3. The whole active film is incredibly thin, just 30 nanometers. That thinness is important for maximizing the interaction with the light's field and keeping propagation distances short.
Okay, 30 nanometer active layer. What's underneath and on top?
Underneath, it sits on a 330 nanometer layer of silicon nitride, Si3 and 4. That's a pretty standard low-loss waveguide material in silicon photonics. And that's on top of an oxidized silicon substrate, your standard wafer base. Then, on top of the SB2SA3 layer, there's a 200 nanometer capping layer of silicon dioxide, SiO2.
Protection.
Exactly. It's not just structural. It serves a really practical purpose, protecting the SB2SE3 from oxidation, making sure the material stays stable over the long term. Absolutely necessary if you want truly non-volatile components that last.
Got it. Structure defined. Now, how does varying this little rod actually implement a phase shift? What's the geometric knob they're turning to tune the weight?
The tuning works by changing the effective refractive index that the guided light mode sees as it passes through that section. The researchers decided to fix the width of the rod at 400 nanometers. That might be related to fabrication limits or perhaps controlling the optical mode profile. The key learnable parameter, the thing they actually changed to represent the weight, is the length of that amorphous rod. They varied this length from 300 nanometers up to 4 micrometers.
And what kind of phase control does that give?
By sweeping the length across that range, they demonstrated achieving more than a pi2 phase shift. And here's the really crucial part. They did this while maintaining near unity transmission amplitude.
Ah, okay. So you get the phase change you need without losing much light.
Precisely. It's a delicate balance. The rod length provides the phase modulation needed to shape the wavefront of the light passing through. But thanks to the intrinsically low loss of the SB2SE3, the transmission stays high. You're not losing signal significantly, which is vital if you're stacking these layers deep.
So the collection of all these rod lengths across the metasurface, those are effectively the network's weights. They're the physical knobs that collectively shape the output light's amplitude and phase. And the whole array you mentioned has a lattice constant of 500 nanometers that sets the spacing between these meta-atoms.
Yes, that defines the periodicity of the structure. Okay, moving up a level to the network itself, the DDNN uses a pretty standard cascaded structure like many neural networks, but here it's all realized physically in the optical domain. The components aren't just abstract math, they're physical layers interacting through wave physics.
Right, so you have your input layer, then a stack of hidden layers, and finally an output detection layer. And in this system, each hidden layer is one of these phase change metasurfaces we've just described.
Exactly. Each metasurface acts like a full-weight matrix, a complete layer of the network. The meta-atoms within it, with their specific fixed rod lengths after training, are the individual weight elements, and the connections between layers, no wires. It's the physical propagation of light diffraction and interference as the light mode travels from one layer to the next.
How do you get the input data, say an image, into a format this optical network understands? We're working with integrated optics, right? Probably the fundamental TE mode at 1.55 microns.
Right. The input encoding starts with pre-processing the image. Let's say you have that 10 by 6 pixel image for the XYZ task. You'd flatten that into a 1D vector, 60 elements long. Then that vector gets encoded directly into the amplitude of the input light field that's launched into the first layer.
Amplitude encoding. Okay, so brighter spots correspond to higher pixel values.
Essentially, yes. This might be done using an array of input modulators, though the paper focuses more on the DDNN structure itself. Choosing amplitude encoding is important because measuring intensity or power at the output is much more straightforward than measuring phase.
And the output. How is the decision made?
At the output end, you have several detection regions, just simple areas designed to measure light intensity, usually aligned linearly. These detectors measure the resulting intensity distribution after the light has passed through all the diffractive layers and interfered. The classification decision is then typically made based on which detector region registers the highest intensity. It's like a winner-takes-all approach implemented optically.
Okay, architecture makes sense. But before we jump into the results, we absolutely have to talk about training. How on earth do you train a physical system like this, modeling light diffracting through multiple complex layers? It sounds computationally brutal. If you have, say, hundreds or thousands of meta-atoms using a standard backpropagation approach based on finite differences, seems like it would take forever. How did they tackle the optimization?
Yeah, that's a critical point. The network is trained using an error backpropagation algorithm, but it's specifically adapted for this kind of electromagnetic optimization problem. It's called the adjoint gradient method. This method is absolutely key to making the design of complex photonic structures computationally feasible. Without it, training these DDNNs would be practically impossible.
Can you unpack that a bit for our audience? Why is the adjoint method so much more efficient here compared to, say, finite differences, especially when you have many parameters, like all those rod lengths?
Certainly. Think about standard optimization. If you want the gradient of your cost function, how much the output error changes with respect to, say, n design parameters, n rod lengths in our case. Using finite differences, you typically run one baseline simulation, then you'd perturb each parameter slightly, one by one, and run another simulation for each. That's n plus one simulations in total.
Okay, so if n is 60 or maybe 196, like in these benchmarks, that's maybe manageable. But if n gets into the thousands or millions, which it easily could for more complex devices.
It becomes completely intractable. The computational cost scales linearly with the number of parameters. The huge advantage of the adjoint method comes from, well, leveraging the physics of the system, specifically solving Maxwell's equations essentially in reverse. It lets you calculate the gradient of the cost function with respect to all n designed variables every single rod length using only two full-field simulations.
Two, regardless of how many parameters.
That's the power of it. You run one standard forward simulation, calculating the electric field, let's call it E, propagating through the structure as normal. Then you run one adjoint or backward simulation. This calculates something called the adjoint field E. This adjoint simulation is like solving the time-reverse physical problem, driven by the error signal at the output.
Okay, so forward pass, backward pass.
Yeah.
Then what?
Once you have both the forward field E and the adjoint field E, the gradient with respect to any parameter can be calculated relatively cheaply. It usually involves an integral over the design region where the parameter has influence, combining information from both E and E. This is standard practice in fields like electromagnetic inverse design or topology optimization. The key is that the computationally heavy lifting, the two full-field simulations, is independent of the number of parameters n.
That's a massive saving. Makes sense why it's essential for these complex designs. What about the specific optimizer they used?
They adapted the standard atom optimizer, which is very common in deep learning, for this mini-batch gradient descent process. Managing the learning rate was also important. They used a decaying schedule, reducing it by a factor of 0.99 each epoch.
Slow and steady.
Right. This kind of slow, controlled decay helps the optimization converge smoothly and avoid getting stuck or oscillating, which can easily happen when you're dealing with a highly nonlinear physics of wave interference. And the cost function they were minimizing. It was the sum of squared errors between the target intensity distribution they wanted at the detectors and the actual intensity distribution the network produced. Pretty standard approach.
All right, so we have the architecture. Non-volatile, rewritable metasurfaces made of SB2 SE3. And we have an efficient training method using the adjoint approach. Let's see it in action. Benchmark task number 1. Simple pattern recognition. Recognizing the letters X, Y, and Z.
Yes, this serves as that initial lower complexity proof of concept. The input data was simple binary images, just 10 by 6 pixels, so 60 input components. But to make it a bit more robust and test generalization, they didn't just use perfect XYZ images. They created a larger data set by taking the base images and randomly flipping the amplitude of single or double pixels, just introducing some noise.
How large was the data set?
This process generated 5,490 images in total. They used 4,590 of those for training, feeding them in small batches of 10. And they kept 900 images completely separate for blind testing afterwards.
Let's talk about the physical device built for this task. What were the architectural specifics? How many layers? How big?
Okay, for this XYZ recognizer, the DD&N was composed of 5 phase change metasurfaces, so 5 hidden layers. Each layer had 60 meta-atoms matching the input dimension. The physical size of each metasurface layer was remarkably small, just 30 micrometers long, and the gap between consecutive layers was 8 micrometers.
So the total device footprint, doing the math, 5 layers plus the spaces, it comes out to around 30 microns wide by roughly 40 microns long.
That's right, it's incredibly compact.
You should pause on that. 30 by 40 microns, that's thinner than a human hair. For a 5-layer neural network, that scale is just hard to grasp sometimes. It's like fitting a complex processing unit into an area smaller than some individual transistors from older tech generations.
It really highlights the potential density of these optical approaches. And at the output for this task, there were 3 linear detectors. Each one was 2 micrometers long, with a 2 micrometer gap between them, positioned to capture the light intensity corresponding to X, Y, or Z.
And performance. How well did it learn this XYZ task?
The results were, frankly, perfect for this task. The network reached 100% accuracy on the training set very quickly after only 3 epochs. This shows the structure could effectively map those input patterns to the right output spots. But more importantly, the blind testing accuracy on those 900 unseen images with the random pixel flips was also 100%.
100% on unseen data. Okay, that gives strong confidence it wasn't just memorizing the training set, but actually learned to generalize from those noisy binary patterns.
Exactly. It's a solid validation for this level of complexity.
Now the critical check, the bridge from the training model, based on that faster diffraction analysis, to physical reality. How did these numerical results compare against a full-wave simulation? Did they run FDTD?
They did. They verified the design using the numerical 2.5D FDTD solver, which is pretty much the industry standard for this kind of electromagnetic simulation. They ran this verification on 90 random patterns from the test set. The result, a 98.8% matching score between the FDTD simulation results and the numerical results from the training model.
98.8% match. That's extremely close.
It is. It's a very strong validation that, at least for this relatively simple task, the diffraction-based model used during training was accurately capturing the essential physics. The design looks physically viable.
Okay, XYZ task successfully handled, high fidelity confirmed. Let's move to a more challenging benchmark, MNIST handwritten digits.
Right. The XYZ task showed it works, but MNIST pushes into classifying noisy, complex, real-world data. They focused on a subset, just classifying digits 0, 1, and 2.
Still, classifying handwritten digits, even a subset, is a significant step up. The variability in handwriting makes it much harder, requires more sophisticated feature extraction by those diffractive layers. What were the dataset specifics and input setup for this one?
Okay, for this 0, 1, 2 classification, they used a larger dataset. 18,623 images for training, fed in bigger batches of 64 this time. The original MNIST images are grayscale, 28 by 28 pixels. They downsample these to 14 by 14 pixels.
Okay, so 14 by 14 means 196 input components. Quite a jump from the 60 components in the XYZ task.
Yes, significantly higher dimensionality. This was again encoded into the amplitude of the input light.
How did the architecture change to handle these 196 inputs? More layers, wider layers.
Interestingly, they used a slightly less deep network for this task. Only 3 phase change metasurfaces, so 3 hidden layers. However, each of those layers was wider, containing 196 meta-atoms to match that 196 component input vector. Because the layers were wider, the overall length of each metasurface grew to 98 micrometers. The separation between layers was also adjusted slightly, down to 7 micrometers.
So the footprint is now roughly 98 microns long by about 21 microns wide. Still incredibly compact, especially given the increased input complexity. That's a remarkably dense little computation block. What about the performance? How did it do on classifying zeros, ones, and twos?
Well, as you'd expect, training take longer. It reached a training accuracy of 92.38% after 140 epochs. The crucial number, the blind testing accuracy and the unseen test data, settled at 91.86%.
91.86% on 012 MNIST. How does that stack up against other photonic classifiers?
That's actually quite competitive. It's in line with, and sometimes better than, other state-of-the-art photonic systems demonstrated for similar 3-class tasks. So performance-wise, it's strong. And again, they performed the FDTD verification. It confirmed the physical viability, achieving a 92% matching score with the numerical predictions. They tested this over 100 random images from the test set.
Okay, 92% match. Still very good, but slightly lower than the 98.8% for the simpler XYZ task.
Exactly. That small dip might be the first hint that as the task complexity increases and the required diffraction patterns become more intricate, the simpler training model starts to diverge a bit more from the full wave reality captured by FDTD.
The researchers also looked into network depth for this MNIST subset, right? How did the number of layers affect the performance? That's always a key question.
Yes, they did a systematic study. They tested architectures with 1, 2, 3, 4, and 5 layers. What they found was interesting. The blind testing accuracy improved significantly as they added layers, but only up to a point. It went from 86.30% for just a single layer, steadily increasing, and peaked at 94.43% for a 4-layer network.
So deeper was better, up to 4 layers. That makes sense. More layers allow for learning more complex features.
Right. But then when they added a 5th layer, the accuracy actually dropped slightly down to 92.50%.
So diminishing returns after 4 layers, why might that happen? More scattering losses accumulating? Or maybe the optimization just gets harder for deeper networks, even in simulation?
It could be a combination of factors. Increased cumulative loss, perhaps more complex interference patterns that are harder to optimize perfectly, or maybe even the training, just struggling to find a good minimum in that higher dimensional space. But the key takeaway, as the source points out, is that since the performance for 3, 4, and 5 layers ended up being quite close, all clustered above 92%, the practical decision comes down to footprint and complexity. An engineer would likely choose the 3 or 4-layer design to minimize the physical size and fabrication complexity, given that the 5th layer didn't offer a significant performance boost.
Okay, this leads us to what seems like the most critical finding in the paper, the point where they hit a kind of scientific wall. We need to talk about the limitations they discovered when they tried to scale up to the full 10-digit MNIST classification task, 0 through 9. What happened then?
This is where the limitations of this specific DDNN architecture really snapped into focus. It was quite dramatic. When they benchmarked the same kind of scheme, appropriately scaled on the full 10-digit MNIST task, 0 through 9, the testing accuracy just plummeted. It dropped down to 76.02%.
76%. I mean, in some machine learning contexts, that might not sound terrible, but for a state-of-the-art approach aiming for high accuracy, that's a major drop-off. It clearly indicates a scalability problem.
It does. But the really telling result, the real red flag, was the fidelity check, the FDTD matching score. What happened there?
Uh-oh, don't tell me.
It completely collapsed. The correlation between the predictions from the analytical model used for training and the results from the full-wave FDTD simulation, that matching score, fell all the way down to just 30%.
30%. Okay, that's disastrous. That's basically saying the training model has almost no predictive power about the actual physical behavior for this complex task.
Precisely. It suggests that distinguishing between 10 different handwritten digits requires generating incredibly complex, fine-grained optical interference patterns at the output. And the simplified diffraction model used for training, while fast, just isn't capable of accurately capturing that level of intricate wave physics. It breaks down completely when faced with that complexity. So the conclusion drawn in the source is pretty stark. These DDNN architectures, at least in their current monolithic form, seem to have a fundamental limit on their computational scale or complexity. The evidence suggests they can physically handle classifying maybe 3 or 4 distinct classes correctly. Beyond that, the physics seem to hit a limit. In fact, they estimate the actual FTTD predicted accuracy for the 10-digit task would only be around 22.8%, given that terrible matching score.
Wow, okay, so just making the network bigger or deeper within the same monolithic design isn't the path forward for more complex tasks. The implication for actually using these is pretty significant then. If you wanted to build something to classify all 10 digits using this technology,
you couldn't just build one big DDNN. The source suggests the way forward would likely involve modularity. You'd need to use maybe 3 or 4 of these compact computing modules operating in parallel. Each module could be specialized to classify a subset of the digits, say one handles 1, 2, another handles 3, 4, 5, 6, and a third handles 7, 8, 9. Then you'd need some logic to combine their outputs.
breaking the problem down into smaller chunks that the optical physics can handle?
Exactly. That kind of structural modularity seems like the necessary next step to tackle more complex, real-world classification problems with this approach.
Let's circle back and really emphasize some of the performance aspects and practical issues discussed. Beyond accuracy, the footprint advantage is huge.
It really is. Let's put those numbers side by side again. The XYZ pattern recognizer, 30 microns by 40 microns. Compare that to a previous comparable fixed function optical pattern recognizer they cited. That one needed 450 microns by 300 microns.
That's more than 100 times larger in area.
Yes, an enormous reduction. Similarly, the MNIST classifier footprint, 98 by 21 microns, is orders of magnitude smaller than prior non-programmable optical classifiers for similar tasks.
And the key differentiator, again, is programmability. Those older, larger systems were mostly fixed once fabricated. You couldn't retrain them. This new architecture combines that incredible density with non-volatile, rewritable functionality. That's what makes it a candidate for more general-purpose optical accelerators, not just single-task devices.
Now, about that simulation to reality gap, we saw the matching score drop from 98.8% for XYZ down to 92% for 012 MNIST, and then collapse for 10-digit MNIST. Let's dig into the technical reasons for this discrepancy between the diffraction-based analysis used for training, like the angular spectrum method, often using FFTs, and the full-wave FDTD verification.
Right. The training model needs to be fast, so it uses simplified wave physics. FDTD is the ground truth, solving Maxwell's equations fully, but it's much slower.
Exactly. The core issue lies in the approximations made by the faster models. They often assume things like paraxial propagation, light rays staying close to the main axis, or they might neglect near-field coupling effects between closely spaced elements. When light diffracts through multiple layers of these densely packed metasurfaces, especially if the features are sub-wavelength relative to the light's wavelength, those approximations start to break down. You get high-angle scattering, complex vector effects, intricate mode interactions, things that FDTD captures because it's a full-wave vector simulation. But the simplified scalar diffraction models used for training just miss them.
So the model used for efficient training isn't perfectly reflecting the real physics, especially as complexity increases.
Precisely. Fast for training, but less accurate. FDTD is accurate, but too slow for iterative optimization of thousands of parameters. That's the trade-off.
To understand the limits better, they ran those parameter dependence studies. Let's start with the lattice constant, the spacing between meta-atoms. How sensitive was the fidelity to that?
They tested 3 lattice constants for the 012 MES task: 300 millimeters, 500 millimeter, which was the design value, and 700 millimeter. The results were quite revealing. While the final testing accuracy was pretty similar for all 3 lattice constants, the FDTD matching score, the fidelity between the training model and FDTD, dropped significantly when they decreased the lattice constant below 500 millimeter.
So accuracy held up, but the model's prediction became less reliable.
Yes, especially for the 300 millimeter case, which is deeply subwavelength compared to the 1.55 micron light. The matching score fell dramatically there. This strongly suggests that when you push into these very subwavelength regimes, like lambda 5 or lambda 6 spacing, the light interaction physics becomes really complex, dominated by a high-order scattering, strong coupling between elements. And in that regime, the simplified diffraction models, like the angular spectrum method, just fail to capture what's really going on. The fidelity tanks.
That puts a practical limit on how densely you can pack these elements while still trusting your training simulations.
Exactly. It constrains the minimum feature size if you want high fidelity between your design model and physical reality.
Okay, what about other parameters? White length, film thickness. Were those as sensitive?
Interestingly, no. The network showed pretty good robustness there. Operation wavelength. They found it worked well across a reasonably broad range, from 1.5 microns up to 1.6 microns, with near constant performance. Accuracy dropped off a bit at longer wavelengths, but overall it suggests it's not hypersensitive to small variations in the laser source, which is good for practical systems.
And the thickness of that active SB2SE3 film.
They tested increasing it from the base 30 millimeter up to 70 millimeter and 100 millimeter. They actually saw a slight improvement in the FDTD matching score with thicker films.
Why would that be?
It's likely because a thicker film gives the light mode more material volume to interact with. This might make the overall wave propagation slightly less sensitive to the fine details and approximations inherent in the diffraction model. The physics might average out a bit more.
But thicker films might have other trade-offs, maybe needing more laser power for the writing process.
Potentially, yes. There's always a balance.
And what about intrinsic material loss? We said SB2SE3 has ultra-low loss, but is it low enough? Especially going through multiple layers?
Because the devices are so incredibly small, the total propagation distance is tiny. The simulations confirm that propagation losses are essentially negligible. They even tested this by artificially increasing the extinction coefficient K in the simulation up to K equals 10 to the 3. That corresponds to a pretty significant loss, about 17.6 divs per millimeter.
Huh.
Even with that high simulated loss, the system performance, both accuracy and FTTD matching score, stayed basically the same for both benchmark tasks.
So the footprint is just too small for material absorption to be a limiting factor here. Good news.
Very good news. And this brings us back to the killer feature, rewritability as the ultimate solution to these modeling and fabrication challenges.
Right. We have this gap between the fast training model and the FTTD ground truth, and likely another gap between FTTD and the actual fabricated device with all its imperfections.
But because the meta-atoms are rewritable using the laser.
You don't have to rely solely on getting the simulation perfect up front.
Exactly. The programmability offers a practical way out. You can train the network using the fast, maybe slightly inaccurate numerical model, fabricate the chip. Then you test the actual optical performance of the physical device. Based on those real-world measurements, you can use the DLW system to go back and fine-tune the individual weights, adjust those rod lengths in situ, correcting for fabrication errors, compensating for modeling inaccuracies.
It allows you to potentially override the limitations of the simulation tools used in the initial design. That seems huge for making these things practical and manufacturable.
It really lowers the barrier. You don't need perfect modeling or perfect fabrication from day one. You can tune it into specification afterwards.
Okay, one last check. Robustness to noise in the input data itself. How did the system cope when the input images were noisy during testing?
They tested this by adding random noise to the input images, up to 20% of the maximum signal level. The results were quite solid. For the simple XYZ pattern recognition task, the accuracy stayed pinned at 100%, even with 20% noise.
Wow, perfect accuracy despite the noise.
Yeah. The FTPD matching score did degrade slightly, dropping to about 85.5% at that 20% noise level, but the classification itself held up perfectly, very robust.
And for the more complex MNIST 012 task?
It also showed good tolerance. The testing accuracy dropped a bit, from the baseline 91.86% down to 84.23% at the 20% noise level. And the matching score went from 92% down to about 81%. So some degradation, as you'd expect, but it still maintains reasonably good operational integrity. It confirms that DDNN can extract the necessary features even when the input signal is significantly corrupted.
Okay, we've covered a lot of ground here, from the nitty-gritty of SB2SC3's refractive index to adjoint methods and FTTD matching scores. Let's try to synthesize this. What's the single biggest takeaway from this entire deep dive into the paper?
I think the major finding, the real headline, is the successful theoretical demonstration of an optical neural network, this DDNN, that is simultaneously ultra-compact, non-volatile, and reprogrammable. They achieve this by cleverly integrating direct laser writing with these SB2SE3 phase change metasurfaces. The architecture hits state-of-the-art accuracies, at least for those constrained 3-class tasks, while absolutely crushing previous designs in terms of footprint, sometimes by over 100x in area reduction.
And the programmability isn't just a feature, it's the key enabler.
Absolutely. That rewritable nature is the crucial practical breakthrough here. It offers a direct path to tackling the persistent simulation-to-reality gap and mitigating the impact of manufacturing flaws. Being able to do online compensation, in-situ fine-tuning, that makes the whole idea of building high-fidelity optical machine learning chips feel much more tangible and scalable than ever before.
So if this work points towards solving programmability in size, what did the source identify as the core scientific hurdle that still remains? Where's the next big challenge?
The core, unresolved challenge, based squarely on their own results, is the fundamental limit on the computational scalability of these DDNNs when structured as a single monolithic block. That dramatic failure on the 10-digit MNIST task, the accuracy crash, the FTTD matching score collapse that wasn't just a minor issue. It points to a real constraint in how much classification complexity a single diffractive network of this type can physically handle. Seems like it tops out around 3 or 4 classes.
So the limitation isn't just the materials or the training anymore. It's embedded in the optical physics of diffraction through complex, scaled-up structures.
That seems to be the case. The researcher's own conclusion leans this way. Simply adding more layers or making the network wider within the same basic design isn't the answer for handling significantly more classes. The viable path forward, hinted at strongly by their findings, seems to be exploring modular architectures.
Breaking the big problem down.
Exactly. Using multiple, maybe 3 or 4 of these highly efficient, compact DDNN modules, each trained to handle a smaller, manageable subset of categories, then combining their results. That kind of architectural modularity decomposing the complex task into optically solvable subproblems looks like the necessary frontier to push integrated programmable optical networks towards broader, more complex real-world applications.